Today we're going to talk about the energy that actually exists in ecosystems. And there's might be some stuff that you've taken in earlier years. Okay, so you've got 110, right? Energy in ecosystems? What's up?
Two questions for you.
Okay.
Number one.
Sure. Okay, so the energy flow. So how do you think? I know what the very first question is. What's the very first question?
All energy ecosystems begin with.
Okay, so let's start with this. You know this one?
Yeah, I just read it.
You can find it in the reading, right? It's right there. Easy way to get. There we go. All energy in all ecosystems begins with the producers, the consumers, the sun, wind energy. And as Lyndon has pointed out, it's the very first sentence of the textbook stuff that I gave you, right? All right, so Leo? Excellent. 100%, right, everyone? Please tell me yes. Are you afraid? I'm a little scared here. It's a good start to the day. Should we just call it quits?
Yeah.
No, I knew you were going to say that. Yes, all energy in all ecosystems begins with the sun. Solar energy is where it all begins, right? So how does solar energy get to Matthew, you ride the bus this morning? What kind of fuel does your bus run on? Diesel? How does the sun's energy get into the diesel in Matthew's bus? It does. It says all energy in all ecosystems begins with the sun. That means that the sun's energy is what got Matthew to school today.
Oil.
Yeah.
Yeah.
The trees grew from the sun.
The trees grow from the sun, absorb the sun's energy. They grow, eventually die, right? End up underground as natural gas or oil, which is then refined into diesel. Did it take a week or two for that to happen? Couple of weeks? Couple minutes. Millions and millions and millions and millions and millions of years. Now you take that, you're better person. Okay, but yes, so it was ultimately the sun that got Matthew to school today. Matthew's future is so bright, his mother calls him son. The sun lights and warms the earth, it evaporates the water, and provides energy to plants. How then do we get energy from coal or gas? I think I've asked that question already. Do we have an answer here? We don't. Did I miss something?
You didn't even put off the stuff. Oh, I guess you just. How do you get energy from?
I need paper in front of me, don't I? Same thing, yeah. So, as Sir Jay's pointed out, how do we get energy from a coal or gas? It's the sun. Can we write this in, or you guys got room, right?
Yeah.
I think I'm going to type, because my writing feels bad today. Sun allows plants to grow, animals eat plants, animals die, and over time become oil. Is that more or less what we said? Become oil or coal or gas. Should I make that a little bit bigger for you? That's good? There we go. The sun allows plants to grow, animals eat plants, animals die, and over time become oil or coal or gas. So one of the problems with this whole system is tomorrow Matthew needs to come to school and he needs more diesel. But how fast are we using that diesel up compared to how fast it's being produced?
It's
Like the rate. Is there still oil and coal and natural gas being produced? Yeah, but it's like crazy super slow, right? Like we will never ever use it, what's being produced today. So that's the problem, is that it's really they call it a non-renewable resource because it's not really being put back, right? A renewable resource, like if you cut down a tree and you plant a new tree, then you sort of renewed, right? You've sort of taken care of that. You put back. Whereas with oil and natural gas and all those fossil fuels, it's not renewable. Okay, so does anyone remember what is the process? I'll hit start here. What is the process called that plants use to take solar energy and create food for themselves? Is it respiration, photosynthesis, biosynthesis, solar synthesis? It's also right there? It's like literally right there. In the reading.
It's both.
Who will be last? How'd we do? Pretty good. Yes, the answer is photosynthesis. About grade 7, I think probably, right? I should probably read from this here. The source of all energy for ecosystems is the sun. It lights and warms the surface of our planet. It gives the energy needed to evaporate water in the oceans and lakes to form rain and snow. Sunlight also provides the energy used by green plants to make the compounds that maintain their lives and serve as food for all other organisms. The sun acts like a distant nuclear fusion reactor, big giant nuclear power plant in the sky. Homer's up there working away, radiating energy out into space. Of the energy released by the sun, only about, I think this is coming up, better be careful. Maybe not. Of the energy released by the sun, only about 1 billion reaches Earth. One over 1 billion reaches the Earth after a journey of about 150 million kilometers. Much of the energy that reaches Earth's atmosphere is filtered out before it reaches the surface. Harmful high-energy cosmic rays, gamma rays, X-rays, ultraviolet radiation are all either reflected or absorbed by chemicals in the atmosphere. Of the energy that penetrates into the lower atmosphere, 30% is reflected by clouds at the Earth's surface. The remaining 70% warms the surface of the planet, causing water to evaporate and generating the water cycle and weather. You guys know about the water cycle, right? Grade 6, maybe?
Yeah, I just thought of it.
You've probably all been to some museum or science place where they see the water cycle. Yeah, I've seen it lots of times. Only a tiny portion, approximately 0.023%, is actually used by green plants for photosynthesis. Photosynthesis is the process by which green plants use sunlight and energy to produce carbohydrates and sugar. So there's so much energy coming from the sun, and we hardly use it at all. Now you need to pay attention when you get your phone. I think I'd actually...
Yeah.
Darn, I hate it when I do that. Oh well, I guess we'll just get good marks. Of all the energy that was released by the sun, how much actually reaches the Earth? Were you paying attention? Is it 100%? Is it about half? Is it around a quarter? Or about 1 billion? I know that I said it, so my goodness, you should all get it right.
Wait,
No clicker. There's a few left. Matthew, got it? Matthew, were you not listening? Or you just haven't pressed enter yet? I'm going to look and see who's messing with me. The answer is about 1 billion. How much energy does the Earth actually receive from the sun? Okay, I'm going to give you some big numbers here. At any moment, the sun emits about 3.86 times 10 to the 26 watts of energy. Do you know what 3.86 times 10 to the 26 means? You guys ever seen Tiny rotation before? This is called scientific notation. It's 3.86 times 10 to the 26. Have you ever seen that before? Some of you have. Where did you see that? Math class? Who taught you? Oh, okay. So then you will know that 3.86 times 10 to the 26, what that means is like 10 to the 26 is like a really big number, right? 10 to the power, 10 times 10 times 10 times 10, 26 times, right? So you move the decimal place, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You move it 26 times. So you're going to have 3.86 and then you're going to have 24 zeros. Okay, add 24 zeros to the end of that number and you'll get an idea of how imaginably large an amount of energy that is. Some of you will still have the old style light bulbs in your home. You know the ones I mean that are hot? You know the kind I mean? Not this kind. Let me show you this kind here. This kind. Not this kind. What's this kind called? This is not incandescent. This is a compact CFL, not Canadian Football League, compact fluorescent light bulb. This is like the fluorescent light bulbs, you know, the big long tube ones like up here. So this is a fluorescent light bulb. This actually says, I can't read it. Can you tell me how many watts that is? It's too small. Can you read it?
I could probably do this.
23. Okay, so this is the thing. This is a 23 watt light bulb. Normally, these kind of light bulbs, like the old style ones, are like 60 or 100 watts, right? What's the difference between 100 watts and a 60 watt light bulb? Don't say 40.
Brightness.
It's the brightness. Exactly. 100 watts are brighter, right, Lily? Not only are they brighter, but they're also, yeah, and they're hotter. Those old style light bulbs give off a lot of heat, okay? They're not very efficient. These ones have no heat at all. So the old style, like a 100 watt light bulb, gives off a certain amount of light. This 26 watt light bulb, because it doesn't give off heat, it gives off the same amount of light as 100, or maybe 60. So it's like 75 of the watts of energy of that old light bulb is heat, which is great in the wintertime, but in the summertime, when your house is already hot, not so good. That's why they went to these. And now they're actually going to those newer style ones, those LEDs, which take up like 2 watts. So they're way more energy efficient, they use up way more electricity. They do cost a lot more.
So like blue lights, right?
Yeah, well, the LEDs are bright, you're right. They said these ones were supposed to last 10 years, and they haven't really been as good as they said they would, right? I have some of those LED ones, and you're right, there's one in my laundry room that's crazy, super bright, but it's nice down there in the laundry room.
But it's like, it's not like that, like glowing, like orangey bright.
Yeah.
It's like that blue bright. That's,
Yeah, I know. Like, that's not too bad. Yeah. So the watts in a light bulb vacuum, this is the same kind of watts here. But a 100 watt light bulb in your house, this is 386,000,000. That's how bright. That's just the Earth energy. That's how much the sun shines on the Earth. Think about all the other energy that's out there. The sun is like a powerhouse, just like massive amount of energy. Most of that energy goes off into space. About 1.74 times 10 to the 17 watts strikes the Earth, which is about 174 quadrillion watts. I guess I had those numbers wrong. That's if there are no clouds in the way. Then 1 square meter of the Earth will receive about 1 kilowatt of that energy. So for like a square meter, like the size of your table, a kilowatt, 1,000 watts. That's how much energy. That's bright. That's a lot of energy. Right? So for 6 hours in the middle of a sunny day, an area the size of a small backyard swimming pool, about 48 square meters, will receive about 288 kilowatts or 1,000 watts of energy, nearly 10 times what the average U.S. household uses in an entire day. So if you've got like a swimming pool in your backyard, about 48 square meters, that's 6 by 8 meters, about like half the size of this room, would receive 10 times what the average household uses in an entire day. All for free, courtesy of the sun. Okay? In the United States, the average daily electricity use is around 30 kilowatt hours per household. Why don't we use more solar energy and less coal and gas energy? Why not? What's cheaper? Coal and gas?
Well, like big money for like solar panels.
Yes, big money for solar panels. although I would argue that to dig the coal up, transport the coal, all that, there's a surprising amount of big money involved as well. It's that we're already used to paying. Right? The cost has come down because all that is built. Now it's just the cost for the actual coal itself, the transportation. Right? But there's still significant cost involved as well, right? So yeah, should we go to more solar energy? What do you think?
Yeah.
There's some people in Dauphin doing that, right?
Yeah.
Where I used to,
Yeah.
used to pay you if you have solar energy.
Yeah, we still do that, yeah.
Like some people just make solar energy, don't even use that energy, just get money where.
Yeah, they just get paid for.
They get paid a quarter of
Yeah.
what they paid for the solar panels, Manitoba.
No, but if you have extra, Manitoba Hydro will buy
I
extra.
believe that's how the program
As a
works.
project, extra, as a treated like a science project in
Yeah.
They, like Manitoba Hydro, like, well, first when you get solar panels, they give you incentives.
Yeah.
And then once you have it, the energy that you get,
It's still, I know that it's, so this is Ludwigton, but there's still about a 15-year sort of time span before you sort of start making some money back, right? And the problem in Manitoba is that our electricity is so cheap to begin with that you're not really, it's going to take a long time to sell it back, right? Because the rate at which we pay for electricity is really low. But in some place in the United States where I've learned, I believe it's Las Vegas or Nevada, where they've actually made it illegal to have solar panels.
Why?
What?
Why?
Why? Because they want to ensure that the energy companies that already exist, they've lobbied the governments so that they have the monopoly. Is it right? I'll leave you to your own opinion, but I think you know mine. Yeah, we should be using way more solar energy, right? If we all just had solar calculators, we could hook up to our house, right? We could power the world with solar calculators. No? That wouldn't work? Those solar panels in town are pretty cool. Oh, yeah. Okay. So, I'm just going to read a little bit more. Photosynthesis is a process. I did that. Many gases found in the atmosphere actually trap thermal energy rising from the surface and directed back to Earth. These gases permit energy from the sun into each permit energy from the sun into Earth's ecosystems, but also act as a barrier preventing energy from leaving. Okay, that's the whole carbon dioxide problem and global warming kind of thing, right? All right, so the albedo effect. Let's move on. You have to read ahead to find out what the albedo effect is.
Oh, I already know
answer the
this.
question about why.
It wasn't really a question. It was more of a spot for you. Did you want me to actually write something down?
No, it's okay.
You do? You're one of those, then. What did I say? Why don't we use more solar energy and less coal and gas energy?
Because the
Yeah, I mean, basically, it's because we're used to it. People don't like change. The infrastructure is already there. There are forces, economic forces, there are companies that are trying to maintain their position, right? The coal and the gas companies don't want to give up to the solar energy companies, right? Do you think the day will ever come when Matthew's grandchildren will ride a solar-powered school bus to school? Possibly, right? I mean, electric cars are certainly, I mean, they were talking about it when I was here. But, I mean, the problem has always been they can't store enough energy, they can't go very far with a charger. Like, if you're going to drive to Calgary, you jump in your car, right? You get yourself to Regina, you go fill up with gas, and away you go, right? Well, if you're driving to Calgary, you're going to stop for 6 hours to recharge, that's the problem. Right? So they got to figure out a way to sort of make that charging quicker. Or maybe people just have to get used to less convenience, right? In the old days, you want to go to Calgary, it might have taken you a week. They could. The problem with that is that you can't, it's the efficiency. The solar panels are not quite efficient enough to power the energy requirements of the car. There's a lot of problems, right? But there's certainly solutions, we just have to work with them. Does that help you in there, Tony? Let's go back to the albedo effect. So the albedo effect refers to a person with no skin color or pigmentation, an African water mammal, a measure of the amount of light that is reflected, or a measure of the amount of light that is absorbed. And Lily's giving me a strange look, but she remembered that she can read the paper and it tells her the answer right there. what is the albedo effect?
Yeah.
Is this going to be a daily thing? You're one of those wanderers that needs to go at 9:30, aren't you? Go really quick, man. Really? You got an answer for me? The albedo effect? Punch it in. Cameron, you got an answer? It's right there. Punch it in.
Albedo.
Albedo. And the answer is C. This is a little harder one, although it is right there in the book, right? The albedo is a measure of the amount of light that is reflected. It says in the book, when sunlight strikes an object, some of the energy is absorbed, some is reflected. Some material reflects sunlight better than others. Albedo is a measurement of the percentage of light that an object reflects. The higher the albedo, the greater the object's ability to reflect sunlight. I have a funny feeling that's the next question. The higher the albedo number, the more light it reflects. The less the light it reflects, the same amount of light is reflected. Right there, I just read it. Okay? And then I think I'm going to ask you for an example, am I right? I really need an extra one of these copies. So I can see what's going on. I must make more copies. For myself, like in the future.
You have to put them in the box
Yeah.
too, so I don't know, so you can
Make a bunch.
I don't know how many students.
You know what? You want to... You've been through all this before, right? More or less, sure. Okay, you find my book. I'll make it better. Leo, got an answer for me? I just have to change the number down in my box because I just go by it. Connor's not here. The answer is A. The more light it reflects. The higher the albedo number, the more light it reflects. So, for the Earth, the higher its overall albedo, the less energy will be absorbed and available to maintain the global temperature. For example, you probably notice how bright snow is when sunlight is falling on it. You guys been out in the wintertime? Anyone?
No.
Anyone been outside in the wintertime? Okay? You've probably noticed that the sun is really bright in the winter because the ground is covered in white snow. Right? In fact, the northern Aboriginals have to wear those sort of glasses, right? The Native American caribou bone story, like, because you can go snowblind, right? Or if you're out in the lake fishing, right? It can be really, really bright too, right? Snow, water have high albedo, right? Very, very high, very bright. Snow contributes to the low temperatures of winter by reflecting energy from the sun back in space. So that's why it's cold. One reason why it's cold in wintertime, because none of that energy is absorbed. It's all reflected back. Snow also delays warming in the spring. Other light-colored or high albedo areas of the Earth's surface, such as sand, hail rocks, and areas of the forest, have a similar effect. I got two things to say here. You know, so in the spring when it starts to melt, and there's those snowbanks, right? And have you ever noticed where it starts to melt? When there's a snowbank, it melts next to the right at the edge, where the ground, where the dirt is. You know why? Because it's warmer, it's darker, right? So where there's dark areas, it's warmer, and the ground is warmer, which means the snow melted. You see all the old people out there dragging the snow around, or spread it around, you ever see that? Melts way faster. How come?
Because they can see more dirt.
There's more dirt. I remember as a kid, because I wanted to play baseball, we'd go out in the backyard and spread the snow around so it would melt faster so we could go to baseball. Right? Okay. The second thing I want to say was, has anyone ever been to Cancun, Mexico? No? Okay, so Cancun is an area in Mexico where the beach is made from seashells. Most sandy beaches are made from, like the sand itself is like small rocks, right? But there's so much coral there in Cancun that the sand is literally, it is white as sugar. It's like a beach of sugar. You know when you walk on the sand at a regular beach, it can be really hot, the beach can burn, right? You can walk on this beach and it is cool as a cucumber. because it's perfectly white. All of the sun's energy is reflected up. It's crazy bright. You have to wear sunglasses, but you can walk on it no problem. I was on a beach in Greece once that had black sand. Guess what? Crazy hot. You had to wear your shoes right to the water. You didn't actually wear your sandals into the water, take them off, and then put them on the side. You couldn't walk on. Any beaches like that in Malta? Black sand or really dark sand?
Not really like that black, but they're really hot.
Really hot. Yeah.
It's like, I've been to volcanic beaches.
Yeah.
It's like where it's actually really black. It's like,
Really hot.
yeah.
Yes. I was in Greece. There's a volcano near Santorini, and you can go up and walk on it. And it was already summertime. It was hot, but same idea. Soil is really, really, really black, and it is just like I was just dripping, just sweat. It was so hot. Yes. Okay, I think I should have given you this answer. Which of these would have the highest albedo? The highest albedo number? Would it be fresh snow, asphalt, shingles, or grass? You guys know what asphalt is?
Yeah,
Like for the roads, right?
like tar and,
Tar and gravel, yeah. Asphalt.
yeah.
Which one of those four would have the highest albedo, do you think? Fresh snow, asphalt, shingles, or grass? This is a thinker. It's not going to say it right in the reading. You're going to have to think. But I've definitely given you the information to get it right. What do you say, Jerry? Oh, you're in. Waiting on Tanner. Which one's going to have the highest albedo? Reflects the most light. Come on, you guys. Oh, almost. Fresh snow. Remember, the more it reflects, the higher the number, right? So fresh snow. Things that are white. Shingles would actually have? Because they're dark, they're black. Okay, give me some other examples of things that have high albedo. I gave you one. Oh, I know for sure I gave you one more. White sand. What would you say, Matthew?
Water.
Water? What about like concrete? Right? Really light concrete? Anything else? Glass? Yeah, probably. Things that are really, that reflect a lot, right? Mirrors, I guess, would have high albedo. You ever see that Mythbusters episode where they claim that like some Greek dude, they defeated, they were being invaded this island, and they defeated the advancing army by holding up mirrors, and they focused all the sun's energy on the boat, and they sunk the boat, they put the boat on fire. You ever see that one? I'll see if I can find it. I think I have it somewhere. Which of these would have the lowest albedo? I know that I've given you this answer. Which of these would have the lowest albedo? Reflect the least amount. How many more questions we got? A little bit? Cameron, which one would have the lowest albedo? The answer is C, black shingles. Right? Really, really dark, like the volcanic rock that we were talking about, right? Things that are black. A black t-shirt. Tanner, you wear that shirt out in the summertime? It's going to be hot. How come? It's black. A white shirt will reflect much more. Other examples? Would grass have,
It would be kind of.
it'd be kind of in between. It's dark. Maybe like tiles, right? If you've got like a tile patio, maybe. Dark cars. Dirt.
The word. Dirt.
Anything that's really dark, right?
Dirt. Dirt.
Oh, how many more have I got? Okay, we got lots more. I just had to look ahead here, see where we're at. Okay. True or false, this one? The snow in the winter contributes to the low temperature because it reflects a lot of heat back to space. Is that true or is that false? The snow in the winter contributes to the low temperatures. True or false? T or F are the top two buttons there on your clickers. I really have to get Jeopardy just like on a loop right here where it just, you should just have a little button.
I work at the Howard so the other day I came over to the children. He's standing and I said, "You're singing that song." So it being he's like, "Don't do that." And I'm like, "Why?" Oh, I was cute.
Got an answer, Jerry? True or false, man?
What?
True! The snow does reflect a lot of heat back to space, so that contributes to the low temperature. That is true. Okay, so here's where you're going to have to do some thinking, okay? Now what I did was you'll see the questions that are on your page there for page 33. I put them up here. So let's talk about volcanoes a little bit. You guys in the elementary school, did you make the baking soda vinegar volcano? Did you make that? Nobody makes those anymore? Very sad. Did you make one, Tanner? It's really just, yeah, it's just a simulation, right? You with me, guys? Okay. So here are some information. 4 volcanoes: Mount Asama, which erupted in 1783, Mount Tamboro in 1815, Mount Krakatoa in 1883, and Mount St. Helens in 1980. Who was alive during Mount St. Helens? 1980. I remember that day. I was about grade 5. I was 12 years old. And Mount St. Helens, I'll get to that. No, let's talk about it now. Mount St. Helens, do you know where it is? Mount St. Helens? It's in the United States. Is it in Oregon? Have you been there, have you?
No, I remember something.
I've seen someone pictures on Facebook or something where someone's been to Mount St. Helens.
I think Oregon.
I'll show you a video. Mount St. Helens is, let me just show you here.
Is it like it's like somewhere in
I think it's Washington. Okay, so here's the map. Look at that, that's kind of cool. It's a long way away. I'll show you where it is. There's Vancouver. No, not necessarily. Where was it now? I lost it. To the left?
It still has your red thing.
I know, I don't see it though.
Scroll out and you see your red thing.
I lost it.
Go up.
Okay, I'll just zoom out and be in the middle. Right there. Right? There's Seattle right there. Okay, so that's where it is. So there's Dauphin way over there. See it? So that's how far it is away. And when I grew up in Neequaw, which is down the road, right? I remember we could not go outside for recess that day because it was so much ash in the air. And when you went outside, everything was just covered in this little fine little ash, dust, everything. It was just everywhere, right? That's a really long way away. That was 1980. Yeah, I'll show you some pictures right away. Okay, so here's my question. Why do you think volcanic eruptions cause low periods of low temperatures? Because after every single one of those volcanic eruptions, the Earth's temperature declined for a little while. In 1783, there was a period of low temperature from 1784 to 1991. That's a time of 7 years. 7 years we had low temperatures on Earth. 1815, for another 4 years after low temperatures. 1883, that was for 6 years, and then Mount St. Helens for like just a year, low temperatures. Why do you think volcanic eruptions cause periods of low temperatures? Say again? Like so much heat in the earth is. Yeah, okay.
It's like ash in the air reflects the sunlight.
Exactly. All this ash in the air reflects all the sunlight back to space, so there's less absorption. Okay? If we were unfortunate enough to have to sit through a nuclear war, because I remember this from the 80s too, because there was heightened tensions back between the United States and Russia back then. We had discussions in school about what would happen in a nuclear winter. With all the ash in the air, it would be really, really cold. Not a lot of sun on the earth, all the plants would die. We would all die. It'd be bad. So the answer is, why do you think volcanic eruptions cause periods of low temperatures? The answer is what? Sergey said it. Yeah, ash in the air would reflect all light and energy. Let's put not all, let's put a lot.
Like, guys.
Off in my head.
Ash in the air would reflect a lot of light, and energy. Is there some way that we could test this theory of Sergey's? How could we test that out? Like here at home? Lyndon, how would we test it?
Fog machine in your room and try sticking a light from one side and see grease.
And measure how much energy is, right? And we could even measure we could have like 2 boxes. How about this? We could have like, let's put a light bulb, two light bulbs. Those don't look like anything like light bulbs. And we have like 2 boxes like this, right? And we'll put a bunch of ash in the air, maybe even chalk dust. Would that work? Right? And then you could put like a thermometer here and measure how much heat. Would that work? Something like that? It'd be fairly easy to prove. In fact, it's right. Which one of these do you think was the largest eruption?
Oh, wait.
7 years. That was 9.
Probably the first one, right?
I think Krakatoa was the biggest.
Krakatoa was pretty big, yeah. I think it was the biggest by volume, perhaps. It probably also depends what time of year this eruption happened, and it probably also depends geographically where it is, too. But yeah, you're right. These two are definitely, I'm pretty sure you're right, Krakatoa was the largest volcanic eruption in recorded history. Yeah. I don't even know where Krakatoa is, to be honest. Is it? Between Java and Sumatra in the Indonesian province of Lampung. Right there.
Island, bro.
Yeah.
It was island.
There we go. Indonesia.
Dude, let's just swim in that water.
All right. Here's some information about Mount St. Helens. This is the one that we have the most information about because it actually happened during sort of our lifetime, our technological era. I'm going to show you the maps here. So here, can you see this one here? I'm going to make this a bit bigger. So here's Mount St. Helens here. This is how much ash was distributed. So you see how far that is. It only shows the United States, but you can imagine that this area here would be like that kind of thing, right? So yeah, here, where would Dauphin be?
Like right.
Like right on the edge there, right? We were just on the edge of it, right? So that's like up to a half an inch of ash, that far away. It's pretty cool. Oh, here's the North American one here. Yeah, it doesn't show it reaching Manitoba, but I definitely remember that day for sure. I think at one time I even had like there was a guy selling it. You could buy like pieces of it. I'll show you some video of it.